In this example, I would like to convert the ordered triple in Cartesian coordinates, or rectangular coordinates, to -2, 1. I'd like to convert it into both cylindrical coordinates as well as spherical coordinates. So with that in mind, converting from Cartesian to cylindrical is the same as the conversion to polar. So first thing I'm going to do is draw this point. So 2, -2 is the only piece that we need to worry about for now, because for cylindrical coordinates it's only x and y that'll be changing. So the point that we would be talking about would be right here, 2, -2. I'm going to try to keep it so that our angle is between 0 and 2 pi. And we should probably try to figure out what the length of the hypotenuse is as well. So, given that we have x and y, let's start by finding r. So r squared is going to be equal to x squared plus y squared. I've defined r in a positive fashion, so we'll go ahead and take the square root and allow it to be positive. X was 2, y is -2, and when we simplify this radical as much as possible, we are going to get 2 square roots of 2. Now, with our other conversions in place, you might already recognize this from the unit circle for when x and y are equal to each other in the fourth quadrant, but just in case, we could also do that the cosine of theta is equal to x over r, which in this case would be 2 over 2 square roots of 2. That would be 1 over the square root of 2, or if you rationalize the denominator, which is encouraged but not needed, you would get root 2 over 2. Sine of theta would be y over r, which is -2 over 2 root 2, or -1 over root 2, or when rationalized, negative root 2 over 2. Here's where knowledge of the unit circle comes in very handy. The angle on the unit circle, measured in radians, where this would be equal to these two coordinates, would be theta equals 7 pi over 4. So expressed as cylindrical coordinates, this ordered triple would be 2 square roots of 2, 7 pi over 4, or -pi over 4 if you prefer, and then z does not change. Z just stays as is. Now that I've created this, next thing I'm going to do is sketch what this point would look like in the RZ plane. So in the RZ plane, r is equal to 2 root 2, which is slightly less than 3, about 2.8. Z coordinate is 1. So that's r, that's z, and the point that we're talking about is right about here. So our reference triangle is going to look like the following. We'll connect it horizontally over to the z-axis. This angle down here is phi, and this distance here is rho. So to calculate rho, we can start by saying that rho squared is equal to r squared plus z squared, or if you want to go all the way back to x squared plus y squared plus z squared, that works as well. Regardless of which one of these you do, you'll get the same result, which is 9. Given that we only want rho to ever be a positive value, that lets us know that rho is going to be equal to +3. So we have a right triangle where the adjacent side is 1, the opposite side is 2 root 2, and the hypotenuse is 3. Unfortunately, this is not ringing any bells from the unit circle, so we're going to have to go with something else. Your options are, you can either say the sine of phi is equal to r over rho, which would be 2 root 2 over 3. You could also say that the cosine of phi is equal to z over rho, which would be 1/3. You could also say that the tangent of phi is equal to r over z, which would simply be 2 root 2 over 1. Taking an arc sine here, an arc cosine here, or an arc tangent here will give you the appropriate angle. If we wanted to leave it in its exact form, we could say that in spherical coordinates, this would be the ordered triple, 3, comma. The theta value does not change, and I verified that in our current textbook it does come second. And then either an arc sine, an arc cosine, or an arc tangent for our third position. So this could be the arc sine of 2 root 2 over 3. This could be the arc cosine of 1/3. Or you can say the arctangent of 2 root 2 over 1. Wow, over 1. People call me Professor Friday over 1 all the time, and I'm like, bro, simplify that answer. So any of those would work for the exact form. If you wanted to round it, you're probably not in a math class. So grab a calculator and just go nuts. Just be sure that your final answer in math class is in radian mode and not in degree mode, because we're math and we like to be stubborn and we don't like to apply things in the real world. So yeah, I said it. Next class period, we'll be talking about how to apply this in the real world. I don't even know if these jokes are like hitting or anything anymore. I can't see your reactions. It's very frustrating. It's okay. I'll get you in class.